Hello friends, let's solve this beautiful exercise we have here. We need to find the shaded area of the figure. We have a large semicircle and inside we have a small semicircle. Alright, now since we need to find the radius of this small semicircle, let's draw some lines to be able to find the radius. I'll erase the shaded area for a moment and in the end I will return it. Pay close attention. The diameter of the large semicircle is 10 because from here to here is 4 and from here to there is 6. So altogether it should be 10. And this marks the center of the large semicircle. So if the diameter is 10, the radius is half, that is 5. The radius goes from here to here. This will measure 5. And from here to there also measures 5. And since this little piece is 4, logically from here to there measures 1. So we erase this here to be able to put the 1 here. Phenomenal. Let's place the dot more or less the center point of the small semicircle roughly located around here. And from this point we will draw a line up to this tangential point. The perimeter of the semicircle and this part which is like the base of the large semicircle. Let's draw a line from here to there. Very well. And as you know, this here is the radius. From the center of the circle to any part of the perimeter is the radius, which we're going to call lowercase r. Very well. When we have the union of the radius of a circle, of a semicircle, with a line tangential to its perimeter, we get 90 degrees. That is, here you will see 90 degrees. Great. Now let's draw a line from the center of the large semicircle to the center of the small semicircle. Perfect. We draw the line and we end up with this here. What do we have? We got a right triangle because here are 90 degrees. This side measures 1. This side measures r. And this side over here, we don't know how long it is, but we're going to call it x. Okay? Phenomenal. Now what are we going to do? We're going to draw a line from the center of the large semicircle to that part over there, which matches the perimeter of the large semicircle, and it also matches the end of the small semicircle. This part here, from the center of the large circle, from the big semicircle, any part of the perimeter is going to be the radius. We already know it's 5. So therefore this will also be 5. Fantastic. Now from here to here is the radius of the small semicircle. So this is going to be fantastic. And here lies the key to the exercise, ladies and ladies. This dialogue here, this guy right here, is the key to the exercise because I can find it in 2 ways. Pay close attention to this red line here that I had drawn. These red lines. It's a line that goes through the center of a string. If you don't pay attention to this part here and just focus on this line here. This line here is a chord that is within the large semicircle. And here is the center of the chord. So if we draw a line from the center of the semicircle to the center of the chord, there will always be 90 degrees here too. So we have 2 right triangles. And we have this common part in the 2 right triangles, which is very convenient. We know then we're going to use Pythagoras for both the red triangle and the blue triangle. So in the red triangle, we're going to use Pythagoras. We know that the hypotenuse squared equals one side squared plus the other side squared. Who is the hypotenuse? The hypotenuse is this part here, which is x. We end up with x squared will be equal to one of these 2 sides. Squared, let's say the side is this one here. We end up with r squared plus side b, which would be this side here, which is 1 also squared. We have found that x squared equals r squared plus 1 squared, which gives us 1. Fantastic, fabulous. We have here an equation in function of these 2 sides. And we're going to see if we can find this same x with this other triangle. We can, can't we? In this case, of the blue triangle, x is no longer the hypotenuse, but becomes one of the 2 sides. The hypotenuse is this one here, measuring 5. So we're going to find one of the sides using Pythagoras. According to Pythagoras, it tells us that one side squared equals the hypotenuse squared minus the other side squared. Who's the side we're looking for? That one. And so I get x squared equals to the squared hypotenuse, which is 5 squared, minus the other side squared, which is r squared. So we have x squared equals 5 squared, which is 25 minus r squared. Phenomenal and fantastic at the same time. Not because we have, well, two things. We have x squared that gives us, this gives us this, and we also have x squared, which gives us this here. Then we can make an equation, we can equate this here, which is r squared plus 1, 25 minus r squared. We move this r squared to the other side, we get r squared, and this r squared, so it becomes plus r squared equals 25. And this one goes on the other side subtracting. Magnificent, we have r squared plus r squared is 2 times r squared. Over here we have 25 minus 1, which gives us 24. Okay, we move on to divides on the other side, but there's 2. I get r squared equals 24 divided by 2. So we know that r squared equals 12, which is great, and we don't need to find the value of r, because with r squared that's enough, and now we'll see why. Well, that's enough because, gentlemen and ladies, the shaded area is the area of the semicircle, which is pi times radius squared over 2. And tell me, how much is it, gentlemen and ladies? What is the square of r? We already have the square here, 12. It's fantastic. Divided by 2. So what do we have? We have that the shaded area is going to be 12 divided by 2, which is 6 by square units. Phenomenal. And we're also going to leave an approximation. The shaded area is approximately 18.8 square units. Fantastic. Let me know in the comments if you liked the video. And don't forget to subscribe and hit like so you don't miss the next challenge. See you another time. Bye bye. Tar.